Hey y'all, so here's what we got going on today. Today is our last day on light and optics. Um, this is the end. This is the end of that. After that, we only really have 4 more classes technically until the last day of school. So after today, next class, we're going to do a series of special topics after this. One I'd like to cover and just touch on briefly is sound. Talking about sound as a wave and how that works and just some basics on that. Then we're going to talk about a little bit about cosmology and astronomy and the formation of the elements. So these last kind of special topics are going to be a lot more relaxed. Mostly just I want you guys to get some of this information, especially these last two and this last one, especially before you guys go to chemistry. I think it would be good for you guys to just have some general background about how those form. But today, what we're going to do is we are going to kind of wrap up and talk about kind of the last bit of optics here. And so to kind of start this off, I want to reference, if you scroll back on Classroom way back to the beginning of this whole thing. Aha! There's this video here that I had posted, and this was when I was cleaning out my classroom, and I walked outside, and there was, of course, you guys all remember this, there was a
Okay, so here I am. So I'm leaving Lester
outside,
Charter School, packed up everything, got the plants in the car.
up in the sky, and
Right
it was like
here.
this like ring around the sun.
And I see, let's see if we can see it.
And there it kind of is. And I was so kind of confused. You can kind of see it, and I went all the way around the sun. And I saw one of these like a few other days later when I was out kayaking. I've seen one recently. The last time we had a full moon, I saw one formed around the moon, and I was really wondering what was going on. And this just kind of got me going. It's like, how do we get like rainbows in the first place? Like, what's actually happening there? So I'd like to start off today by just talking about rainbows in general. So if we look at like a rainbow like this, there's a few things that you'll notice. Number one, the sun is always going to be behind you with a kind of standard rainbow, and there's always going to be some kind of like a cloud or rainstorm in the sky. So you're going to have raindrops that are somewhere in the background here, and the rainbow is kind of like somewhere. If I were to diagram it here, if I could draw a diagram real fast. Oh my gosh, there it is. Boom, there's your diagram. Here we go. I'll go right there. So if we draw like a little diagram about this, right here you have the sun kind of behind you, here you have the rain cloud, and then the rainbow kind of forms right in this area right here. So how does that happen? Well, because of these elements that we need to have the sun behind us and the rain cloud here. One thing that you guys may have noticed is that there has to be something going on with these raindrops. Now this is kind of what a raindrop actually looks like. It's pretty much just like a circle. So I'm gonna move my magnified raindrop there to the front of the rain cloud. If we think of it, we have light rays coming from the sun that are coming down, and they are striking, right, these raindrops. Okay, and as we know, when light goes from one medium to another, so from air to water, something can happen, right? It will slow down. So if we look at a ray of light kind of entering at this upper part here, what's going to happen is this upper side is going to slow down, or this lower side is going to slow down first. So it's going to turn it a little bit to the right. So if we kind of draw what's going to happen here, it's going to actually bend and go like that. All right, so it's just going to bend slightly within there. And then as it exits, right, it's going to do the same, right? It's going to exit, and this side's going to speed up first. So it's going to kind of cause it to bend this way, right? So we get our light that's kind of going from the sun through our raindrop and then out to there. Well, the question is like if this is, for example, just a red wavelength of light, how is it that that wavelength of light is coming back so that I can see it, right? How is it coming back to my eye? Because in this case, it looks like it bent through that raindrop, but it's still going that way, right? It's still going away from me. So how is it that I can actually see it? Well, if we open up kind of this PHET modeling software, and we see here we're going from air, in this case, to glass, right? And we'll want to go ahead and change that. We want our object to be water, right? And then so here's our raindrop. It's water, so it's going from air to water. And we see exactly this. This ray of light comes down from the sun, and this is white light, so this is all the wavelengths. Comes down from the sun, it bends, it refracts, and then it refracts again when it exits the raindrop. But this is not going to direct it back towards where we are, which is over here. So what's actually happening is here we're just looking at the refraction. We're just looking at the transmitted light, the light that's passing through the light, or through the raindrop. But in reality, we also know that there is reflected light. So if I turn on the reflections, you can see that yes, there are actually wavelengths of light that are bouncing off of the back of this raindrop, right? There's some internal reflection. It's not total internal reflection, but there's some internal reflection that bounces back. And we see it does it again. And there's some there. There's some reflection off of the surface. So there's light waves actually being kind of reflected and refracted in all sorts of directions around. But this is the one that's going to be most useful for us talking about our rainbow, because this is the one that's actually coming back towards our eyes. Okay, and you can actually see those light waves are actually starting to disperse already, right? They're starting to separate based on their wavelength. Okay, so we get if you can kind of see, the blue is refracted the most, right? Because it's got the shortest wavelength, or the violet is, and so it's on top, right? It gets bent the most as it's refracting, whereas the red is the least. So this is what we end up having, and if I kind of move this, you can kind of see that the angle changes. But one thing I want you guys to pay attention to is looking at the angle this is coming out at relative to the angle it's coming in at. Notice right here it starts out very small. It's a small angle between going in and coming out. And there it gets bigger and bigger and bigger and bigger. But then there comes a point where it actually starts to come back the other way before it just totally disappears and misses. Right? And you get some cool stuff right around there. But the angle kind of reaches a maximum right about there-ish. Right? And if we actually put in my protractor, there's that 0. So if I move this in here and I put that there, you'll see that that angle of maximum is right around about 40 degrees, right? Where it's the maximum kind of bend, right? The maximum angle that we can get there. And there's a good example. I've kind of linked to this site here, but this is a good example on this site called Atmospheric Optics. They talk all about rainbows. Really cool. Like if you guys kind of go through and look through this whole thing, it is amazing. Like it covers just about everything that there is with all sorts of atmospheric optical phenomena. But this kind of talks about how as I change this angle that it's coming in at, and I look at the angle that's leaving, you can see down here what we actually get. And you'll see, you'll see that it kind of maxes there, right? And then from there it actually gets kind of smaller and smaller again. So that also happens to be right there, 1 in 37.5. Well, if we look at this extra little angle in there, right, that ends up being about 40, 37, that'd be 42.5-ish degrees, right? So pretty similar to what we're seeing over here. And so that angle happens to be, you'll notice it's still reflecting light back at all these other angles, right? But notice it's also not dispersing as much, right? We're kind of getting more of that light mixing. It's not refracting quite as much at the same angle, so it's not quite dispersing as much. But at that 42-ish degrees, right, you'll see there's a good bit of dispersion, and that's actually where these wavelengths are kind of going to end up being the most pronounced, right? It's not that there's light not bouncing back at those other spots, but this is where they're going to be the most pronounced. That's where we're going to kind of see them. So if we look here, we can kind of diagram this in our drawing here, right? What happens is inside this raindrop, right, we know that there's some light that actually kind of bounces back here, right? Some light bounces back, and based on the angle that it's bouncing back at, right, it kind of refracts and it bends back towards our eyes, right, just like that. And so this would be an example for like a red wavelength, okay, as it kind of goes through. Now, as we mentioned, blue wavelengths of light, right, and purple, right, they actually refract a little bit more. So if I had a blue wavelength coming from the same raindrop, right, notice it would be hitting above my head. I wouldn't actually be seeing it. So in order to see this blue wavelength, I actually need another raindrop. Oh, come on. No. There we go. I need another raindrop that's below this previous raindrop. And those blue wavelengths of light, of course, come in. They come in at just, the ones that come in at just the right angle. They bounce off the back. They bounce off of there. And then they refract, and those blue wavelengths come towards my eyes. So you'll actually see that the red raindrop, the wavelengths are, the red wavelengths are coming from a raindrop that is above those of the blue. So if we actually look at our rainbow, you'll notice that red, right, those wavelengths of light coming, those red wavelengths of light coming from those raindrops are above those of the blue, right? And that's how we get this whole spectrum like this. Now you'll notice also, if we go back to here, right, that at, you know, lesser and lesser angles, we get essentially just like a jumbled mix of white light, right, that's coming back. So above blue, above this angle, there's going to be actually white light. And if you look at your rainbow, right, you'll notice that below blue, right, thinking of raindrops that are here below, right, if I also have another raindrop, we go. If I have another raindrop that's like down here, for example, right, then the light that's coming from it, right, so going from the sun to that raindrop, it's going to, of course, refract, and bounce back. But this light that's coming to us from anywhere below this blue, the light that's coming from us there is going to be just kind of like jumbled white light. So things are just going to appear brighter. And so that's what we actually see with a rainbow, is you'll notice that there's kind of this dark, in here we have a double bow, but everywhere above the rainbow is kind of like this dark color, and then everywhere below is like a little bit lighter, right? And that's because beyond red, beyond that certain angle, right about there, no light kind of reflects back towards us, right? So that area actually ends up appearing quite a bit darker. So that's that. That's actually how we end up getting a rainbow. Now, a nifty feature of this is that, of course, this is just looking at kind of like one slice of the rainbow. But the way this actually happens is in 3 dimensions, it happens in a cone, right? So you can actually, and that's why we end up getting this bow, is that's like one sliver of the cone, right? And then the bottom part of the cone is cut off by the ground. But if you can actually get up above the ground, like this, right? This is taken from a plane over Australia. You can actually see the full circle. You could also do this with like a garden hose on a mist setting. Once again, it's like the sun has to be coming from behind you, right? So the sun's coming from behind. You kind of have your mist or hose, and the light goes, into those raindrops. It kind of refracts and reflects back towards your eyes in this full circle, which is pretty cool. And so it's not actually ending up being cut off by the ground. And perhaps you guys have seen this before. So that's how you get a rainbow. And of course, you can really see that distinct dark band there, and everything inside is light because you're getting kind of more white light that's being reflected back there. So pretty cool. And there's also some other stuff with this double rainbow, that second rainbow on the outside. What's happening there is, if we go back to the simulation, if I actually have it entering here like this from the bottom side of the raindrop, you'll notice, do you see this kind of, it goes in, it reflects, or it refracts, reflects, and then refracts out, and you get this little beam here. That guy is what gives us actually that double rainbow there. Which is kind of cool, and you can see, once again, it's like there's that point where it kind of reaches an angle and goes there. So that's the angle for that double rainbow. It is reversed from our regular rainbow. So if you actually look at it, instead of going from red to blue, it goes from red to blue that way. So that's that. I've kind of linked to this site, and I've also linked to this video by Physics Girl that talks about how rainbows form in a far more succinct and short and sweet way than I do. But it's all essentially kind of the same information. But a short little video if you guys want to check that out. Now, if we look back to this thing, though, there's one issue, right? This little rainbow that I saw around the sun, we actually call that a halo, not necessarily a rainbow. But the issue here was that the image itself was between the sun and me, right? So instead of like here, where the sun is behind, I'm between the sun and the rain cloud, the sun and the image, and I'm getting that reflection back. In this case, it's more like this, right? Here I am, there's the sun above me, and I'm actually seeing a rainbow here in the sky, right? So what's happening there, right? How does that work to where, I get that? Well, one thing you'll notice is that you'll only kind of see these, or you'll usually see these when you have kind of these thin, wispy cirrus clouds in the sky. And these cirrus clouds are actually made up of little fine ice crystals. They've also got great information on this atmospheric optics site, and I linked to this as well. But this is called a 22-degree halo, right? And it's formed with these cirrus clouds in front of the sun. You'll actually see these all the time. You can see them from the moon, from the sun. It's really cool, and it always forms there's a 22-degree angle between kind of the sun, this reflection, and you, right? So similar to with the rainbow, there's that about 42-degree angle, right? In this case, it's a 22-degree angle that it's reflecting back to you at. So if we look and we think about what's just happening here, right, in some way, right, we know that we have, right, these wavelengths coming from the sun, and they're coming, one thing to keep in mind is, of course, is that light is coming from the sun in all directions, right, not just those. But some of those happen to come in at just the right angle, and they strike this cloud, right? And this cloud is made up of all these ice crystals, and we've got this magnified little ice crystal here. So if I kind of select this guy, oh no. right, and I move it over here, right, and I'm actually going to need to rotate it a little bit as well. All right, there we go. So if I put this guy in here, right, so there's our magnified ice crystal. Well, we can kind of approximate this in this PHET simulation using, instead of that, we'll use this guy, right? And if I actually kind of turn this guy like this approximates about like one side of that kind of hexagon. It's close to it. It's not perfect by any means. Now, one thing of note is that the index of refraction of ice is a little bit greater than that of water. Right? It's not quite up to glass, but it is to kind of make up for the fact that this angle is a little bit off. But what happens is this light comes in, and it actually, it bends and refracts, but at a lesser angle than with that circle. Right? It does indeed reflect, and there's all sorts of crazy reflections that happen in there as well. But it does, in this case, it refracts, and that's what we're looking for. We're looking for the sun, clouds, and then me kind of somewhere down here. Right? So you'll see it actually kind of bends and refracts there. Once again, on this site, they've got a great kind of example of this where they kind of illustrate how, once again, that angle kind of reaches a maximum or a minimum at about that 21.7 degrees. Right? And then it gets greater. So then that's its kind of minimum is right around that 22 degrees. And so that's actually where it ends up being the strongest or the brightest kind of light. And so what happens, in this case, it just passes through. So here we've got it going through. If I go to here, so it's passing through. Let's see which side, and it'll bend something. I think I might have moved this guy to the wrong spot. So let's go ahead and move this guy over to here. There we go. And it's going to bend through like that, refract. And then it's going to, of course, come back and refract out. And it's going to come to my eyes, right? And the same is going to happen with the blue lights. In this case, if we do that with the blue. Oh, there we are. So if we do the same thing with the blue lights coming in, right? And it comes in, and in this case, the blue light, it actually refracts a bit more. Right? And you can see that that blue light's going to miss my eye. Right, so what happens is we have another crystal over here, and so then the blue light ends up being a little bit further outside of the sun in the sky. And the main thing that we can actually see with this one is the red wavelengths. We don't really see the others as much. If you ever see one of these, you mostly see that red, and then you see some of the others kind of fading outwards from that red band. But that's, once again, it's like as these drops get farther and farther away, that's what we end up seeing. So that explains how this all happens. And of course, you guys could talk about how, we get those lights being emitted, or those electromagnetic waves being emitted from the sun in the first place, right? We've got these charged particles that are accelerating and moving around in the sun and emitting all these wavelengths of light. We've got a lot of infrared, what's called blackbody radiation. So because the sun's really hot, it emits like this glow, and that glow happens to be centered around the visible light range of the spectrum, specifically kind of shifted towards the yellow kind of wavelengths of light. But it's emitting all sorts of ultraviolet radiation, or all sorts of electromagnetic radiation, all these electromagnetic waves. Some of them are not able to pass through our atmosphere. Others, such as visible light, are, right? They can interact with different mediums when they pass into them. Sometimes they're absorbed, sometimes they pass through, they're transmitted, sometimes they're reflected off, as we get here. Depending on how they're transmitted or how they pass through, right? They can actually reflect off of things, they can refract, they can bend through things as they slow down, entering different mediums. And eventually they can come to our eye, right? And our eyes have these specialized cone cells. We've got red, green, and blue cones, or long, medium, and short cones that allow us, they're stimulated by these different wavelengths of light. And depending on the stimulation of those, right, that causes our brain to actually see and perceive these different colors, right? So that's like the whole story of how it happens, kind of covering everything that we've talked about. And it really is a beautiful thing. That's one of the best things about it, is that it's like, because of all of this stuff that's happening, it just happens on its own, it is the way of the universe, it allows us to see something that's just kind of beautiful and pretty, and kind of gives us pause. It's unique. But it can all be explained by, the physics that you guys have learned. So that's that. Make sure you guys kind of check out those links if you guys want more information. Unfortunately, I'm so sorry about this, but I made a quiz for you guys. It's 30 questions. It's just for participation. I just want to see, it's going to give me hopefully a glimpse of how much you guys have remembered and retained. Hopefully you guys can kind of take it as a challenge to see like how well you can do, but it's no pressure, right? If you get an F, you're still going to get an A in the grade book. It's just more for me to kind of see. So hopefully you guys have enjoyed this whole unit so far and enjoyed learning about light, and hopefully it was smooth and not too terrible. And yeah, I'll see you guys next class.